Record. All right, everyone. I just received an email last night telling us our final exam room location. So on June 25th, let me write that out. And I already sent out an announcement. So on Thursday, June 25th, that's our final exam. Oh, dang it, I forgot I already wrote it right there. It's from 10 a.m. to noon in building UC1 in room 124. So building UC1 is kind of, if you've never been there before, it's really kind of hidden away on the other side of campus. So because I remember my very first time, I caught all kinds of trouble finding it. So if you're not familiar with it, I would recommend at least one day beforehand driving around and kind of locating it, because it is really kind of tricky to find the first time. Okay, so the final exam review module has been opened up so you can prepare, even though we have a chapter left to go. I just open it up so you can start on that. And it's a departmental final, which means the math department, they make it up. I have no say-so as to what's going to be on it, have no clue. But just from past classes, everyone has always said that the reviews were very close to what's on the actual exam. So if you can kind of go over the reviews, it should prepare you pretty well for it. And I've even had some people say, some of the same questions on the review appeared on the final. So you never know. All right. And again, an announcement has been sent out. So even if you didn't write this down, it's already there. And they do have the rooms reserved like back to back to back. So we have from 10 a.m. to noon exactly. So if you oversleep and you come in at 11:30, I cannot give you additional time, because at noon, whether you're finished or not, we have to be out of there. So try to not arrive late. All right. So we are going to go ahead and finish out chapter 4 by looking at section 410, which covers antiderivatives. Okay, so luckily, if we keep this pace, we are a little above or a little ahead of schedule. So it should be able to allow us a few days between the very last class and the final. So I'm just hoping we can keep on this pace and finish up and give you at least a couple of days to study and prepare. So it's not like very last class and then final the next day. So I don't like that. I like to kind of have a few days to prepare. Okay. So with antiderivatives, it's pretty much like the name says, it's kind of the way to undo derivatives. So think of this way. Let's say if we know that the derivative of x to the fourth power equals 4x to the third power, just using the power rule for derivatives. Okay. So with antiderivatives, we don't go from derivatives to our derivative, we go from the derivative to our original function. So we use the antiderivative. Well, we don't even need that dash. To reverse, or you can say undo, the derivative. So the definition of an antiderivative states that if we know that f prime of x is a derivative, but for an antiderivative, you will normally see an uppercase f of x. Not always. Sometimes they will have that as a regular function, but in a lot of cases, they'll use that for your antiderivative. Okay, and it is an antiderivative of the function f of x on some interval from a to b. And we know that some function we'll call uppercase g of x is an antiderivative of f of x on the interval from a to b in the form where g of x is equal to the antiderivative of our function f of x plus c. Okay, now the notation for an antiderivative is just the integral symbol. Notation for antiderivatives is the integral symbol. And it really looks like an elongated S. And a lot of times, just writing it really, really fast, it'll look different ways, but for the most part, it kind of looks like that. So that's the antiderivative of f of x with respect to x. So you can read it that way. So we know that it reads the antiderivative of f with respect to x. Or you can read it as the indefinite integral of f with respect to x. Okay. Now that plus c, believe it or not, is very important. As a student, I lost a lot of points on exams because I forgot that plus C. Of course, you're taking it online, so you don't have to worry about that. They'll usually tell you don't worry about the plus C. But if you're writing it by hand, that plus C is very important. And I'll leave that up for a second, and I'll explain why on the next page. All right, anyone still writing? All right. So why is the plus C so important? Okay, so if you notice, let's say if we have the derivative with respect to x of x to the fourth power plus 8. Well, that's equal to 4x to the third power plus the derivative of 8 is 0. So that disappears. Same thing if we have the derivative with respect to x of x to the fourth power minus 27. That's still 4x to the third power because the derivative of that constant is 0. Or just the derivative with respect to x of x to the fourth power by itself. Still 4x to the third power. So that plus C just acknowledges that, okay, each of them could have a different constant, or that constant could be 0. So that's why that plus C. So the plus C acknowledges the, hope I spelled acknowledge right, if I did. Okay, acknowledges the fact that a constant could be present. And in some problems, we actually will be solving for that constant. All right, any questions on that so far? All right. Okay, so let's look at some of our antiderivative formulas. And I'm just going to split this down the middle and show you how they compare to our differentiation formulas. Okay, so we already know that the derivative of a constant that we'll call C is equal to 0. Okay, so what if we take the antiderivative of both sides? Well, we know the derivative and antiderivative cancel each other out. So we're left with the antiderivative of 0 with respect to x is equal to c. Okay. Or what if we have the derivative with respect to x of some constant, we'll call constant k, times x. Oops, there we go. Well, we know the derivative of x is just 1, so that'll be k times 1, which is just that value, k. Okay. But if we take the antiderivative of both sides, we know the derivative and antiderivative cancel each other out. So we're left with the antiderivative of k with respect to x is equal to k times x plus c. And we kind of separate these a little bit. Excuse me. Okay, and if you remember the derivative of some constant k times some function f of x is just that constant k times f prime of x. So again, if we take the antiderivative of both sides, and I'll factor the k on the right on the other side, the derivative and antiderivative cancel each other out. So we know that some constant k times the antiderivative of our derivative f prime of x with respect to x, then that antiderivative and that derivative cancel each other out again. And that's just equal to that constant k times the function f of x plus c. Okay, and same thing if you have the derivative with respect to x of some function f of x plus or minus some function g of x with respect to x. Okay, well, we know that that's equal to the derivative of f of x plus the derivative of g of x. And we move that equal sign up a little bit. Here we go. Well, it's the same thing with antiderivatives. The antiderivative of f of x plus or minus g of x with respect to x, same way you just distribute the derivative, you can just distribute the antiderivative. So that's equal to the antiderivative of f of x with respect to x plus or minus the antiderivative of g of x with respect to x. And you'd have a plus c for this one, a plus c for this one, so you just combine them and have your own constant. So you can kind of put the constant at the end. Okay. And we also know that for derivatives, the derivative with respect to x of x to the power of some real number n You just bring that number down to the front times x to the power of n minus 1. Okay. But if we had the antiderivative of some x to the power of n with respect to x, that's going to equal x to the power of n plus 1 divided by n plus 1 plus c. Okay. We also know that the derivative of the natural log of x is equal to 1 over x. So if we take the antiderivative of both sides, those two cancel each other out. So that gives us the integral of 1 over x with respect to x is equal to the natural log of x. Plus c. Okay. So if you know all of your derivatives, most of your antiderivatives can still be figured out using those. Not all of them, but most of them. The only ones that might give you a little bit of trouble as far as comparing one to the other are your trig antiderivatives. And that's only because some of them have different, I guess you could say, techniques from finding the antiderivative. But we'll look at those shortly. Okay, and the same way, we know that the derivative with respect to x of the natural log of some function of x, we've already proven that that's equal to g prime of x divided by g of x. So the derivative of that argument divided by that argument. So if we take the antiderivative of both sides, we know the derivative and antiderivative cancel each other out. So that lets us know that if we have the derivative, the antiderivative of g prime of x divided by g of x with respect to x, that's equal to the natural log of that function g of x plus c. And probably the easiest one to remember, the derivative with respect to x of e to the power of x is just e to the power of x. Okay, so we already proved that one. So if we take the antiderivative of both sides, we know that cancels out with the derivative on the left. That means the antiderivative of e to the power of x is equal to e to the power of x, well, with respect to x. E to the power of x plus c. that's the derivative of e to the power of some function of x other than just x by itself. So we'll call that g of x. Okay. We've already proven that that's equal to e to the power of g of x times g prime of x. So we take the antiderivative of both sides. We know the derivative cancels out with that antiderivative. So that leaves us with the antiderivative of e to the power of g of x times g prime of x with respect to x is equal to e to the power of g of x plus c. And we'll continue the rest of those on the next page. Yes.
For the antiderivative of the sum and difference of f of x and g of x, wouldn't that be the sum and difference of f prime of x and g prime of x? Since we've taken the derivative of the functions. Or am I misunderstanding?
Oh, yep, with that one. Yep, I did forget that. Thank you. Yep, so it should be the integral of f prime of x and g prime of x. Right. So that integral and derivative cancel each other out and left f of x. Thank you. And that would actually just give us f of x plus or minus g of x, since the derivative and antiderivative cancel each other out, which is where we started off there. And we don't really need that respect to x, since it's just f of x and g of x. I mean, wouldn't hurt, but honestly, it's a little unnecessary. So we'll just make that f of x plus or minus g of x, since we already know they're with respect to x, plus c. So you can kind of see here where everything is pretty much undone between derivatives and antiderivatives. So that's kind of their relationship. All right. Now let's look at trig functions. So we have our derivative. Move that over a little bit. There we go. And we have our antiderivative. Okay. Now, most of the trig functions share the same process as far as finding the antiderivative. Only a few of them do not, and we'll look at those two. So if you have the derivative with respect to x of sine of x, we already know that's cosine of x. We've proven that one. take the antiderivative of both sides, where the derivative and antiderivative cancels out. That leaves us with the antiderivative of cosine of x with respect to x is equal to sine of x plus c. Same thing, we know that the derivative of cosine of x is equal to negative sine of x. And if we take the antiderivative of both sides, and know the negative antiderivative of sine of x with respect to x is equal to cosine of x. And instead of plus c, we'll say plus constant. We'll call it constant number 1. Only because now we're going to multiply each term by negative 1. So if we multiply the left side by negative 1, that just gives us the antiderivative of sine of x with respect to x is equal to negative cosine of x. And we multiply this constant by negative 1, that'll just give us another constant, so we'll just call that c. And we know that the derivative with respect to x of tangent of x is equal to secant squared. So if we take the antiderivative of both sides, those two cancel out. So we know that the antiderivative or integral of secant squared with respect to x is equal to tangent of x plus c. And we know the derivative of secant is equal to secant times tangent. Take the antiderivative on both sides. On the left, the derivative and antiderivative cancels out. So that leaves us with the antiderivative of secant times tangent with respect to x is equal to secant. Secant of x plus c. Okay, and we know that the derivative with respect to x of cotangent of x is equal to negative cosecant squared. So once again, we're going to integrate both sides, where we know that derivative and antiderivative will cancel each other out. So we know the negative antiderivative of cosecant squared of x with respect to x is equal to cotangent of x plus some constant we'll call c number 1, because once again, we're going to have to multiply or divide each term by -1. Which gives us the antiderivative of cosecant squared of x with respect to x is equal to negative cotangent of x plus c. Okay. And we know that the derivative with respect to x of cosecant is equal to negative cosecant times cotangent. So taking the antiderivative, and of course we know we're going to have to divide all the terms by -1, and that will have the integral of cosecant times cotangent with respect to x is equal to negative cosecant of x plus c. Okay. So if you notice, we don't have an integral of tangent or an integral of secant. We have secant squared, but that's an entirely different process to find the integral of secant than it is secant squared. Okay. Now here, the integral of just tangent of x with respect to x is equal to negative natural log of cosine of x plus c. And I'll show you the proof of that one in a second. Let you finish writing. Okay, so if you remember, we know that tangent of x, we can rewrite that as sine of x divided by cosine of x. Okay, so what if we let our g of x equal cosine of x? Well, the derivative of cosine is negative sine, so that means our g prime of x is equal to negative sine of x. So we're looking for the antiderivative of tangent of x with respect to x. We can just rewrite that as the antiderivative of sine of x divided by cosine of x with respect to x. Now, the only thing is, for this to be g prime of x over g of x, this would have to be negative. So we can't just randomly put some negative in there. So we'll put a negative here, and to counter that, we'll put another -1 here. So -1 times -1 is just positive. So what that gives us is the negative antiderivative of your g prime of x divided by your g of x with respect to x. Okay, and we already know that the antiderivative of g prime of x over g of x is just negative, in this case, the natural log of your g of x plus c. And since g of x is equal to cosine of x, we could just rewrite that as the negative natural log of cosine of x plus c. Okay. So again, you don't have to memorize the proof or anything. This is just showing you where it came from. And we'll continue on the next page. Excuse me. All right. Anyone still writing? All right. Okay. And it's pretty much the exact same thing for the antiderivative of cotangent of x with respect to x. You rewrite that as cosine over sine and do the same process over again, and you'll end up with positive natural log of sine of x plus c. Okay. We know that the antiderivative of secant of x with respect to x is equal to the natural log of secant of x plus tangent of x plus c. And the antiderivative of cosecant of x with respect to x is equal to the negative natural log of cosecant of x plus cotangent of x plus c. So if you notice the pattern with those antiderivatives, at least the last four, they're very similar. Okay, so we know, let me just move this up here just a little bit, that the antiderivative of tangent is negative natural log of cosine. And cotangent, which is its cofunction, is positive natural log of sine. So if you notice, tangent is negative, cotangent is positive. And with this one, secant is positive, cosecant is negative. So the cofunction antiderivatives will always have different signs. If you notice here, the antiderivative of tangent is natural log of cosine. Cotangent is natural log of sine. So even their arguments are different, are its opponent's cofunctions, or its cofunctions. Same with secant and cosecant. With secant, it's natural log of secant plus tangent. With cosecant, it's negative natural log of cosecant and cotangent. So they all still have that relation there. All right, anyone still writing? All right. Okay, and it's pretty much the same idea for our inverse trig derivatives. And our inverse trig antiderivatives. Okay. Well, we know that the derivative with respect to x of sine inverse, we know that's arcsine or sine inverse of g of x is equal to g prime of x divided by the square root of a squared minus that g of x squared. And remember, arcsine is also sine inverse. Just another way to say it. Well, the antiderivative on both sides. We know the antiderivative of g prime of x divided by the square root of a squared minus g of x squared with respect to x is equal to arcsine of g of x plus c. And the same thing for the derivative with respect to x of just arcsine of x. We know that derivative is equal to 1 divided by the square root of 1 minus x squared. So we took the antiderivative of both sides. The left side derivative and antiderivative would cancel out. So we know the antiderivative of 1 divided by the square root of 1 minus x squared with respect to x is equal to arcsine of x plus c. And remember, this is just another way to write sine inverse of x. Okay. And we won't go through all the derivative and antiderivatives for the rest of them. We'll just write the antiderivative formulas for them. So we know the antiderivative of 1 over 1 plus x squared with respect to x. That's equal to arctangent of x plus c. Same thing if we had the antiderivative of g prime of x divided by a squared plus g of x squared with respect to x. This would be 1 over a times arctangent of g of x divided by a plus c. Okay, let's see if I can close that up a little bit. Here we go. And with the arctangent, the only difference is your g of x is x and your a is 1. So that's just x over 1, which is how you got the x. And here, 1 over 1 would just be 1. And last but not least, let me give this a little more room because I already know I'm going to run out of space for this one. I should have had this one a little bit shorter. We have the antiderivative of g prime of x divided by the absolute value of g of x times the square root of g of x squared minus a squared with respect to x. And that's going to equal 1 over a times arcsecant of g of x over a plus c. Still almost ran out of room. Okay, so yes, it is a lot to remember, but just a little bit of association with the derivatives that hopefully you already have a little bit of a grasp on, or really big grasp on, will help you remember the antiderivatives. All right. So let's say, for example, we wanted to find the antiderivative of f of x equals 3x. Okay, so with this one, you're going to have to remember two antiderivative concepts. Antiderivative of some function k times f of x with respect to x. You can actually factor out that constant k. same way you could with the derivatives, and the antiderivative of x to the power of some real number n with respect to x is equal to x to the power of n plus 1 divided by n plus 1 plus c. Oops, clean that up a little bit. So that's just a little note. Okay, so if we're looking for the antiderivative of 3x with respect to x, we can get that 3 and just bring it out to the front, which is what we did here. And that x, we can rewrite that as x to the first power. You don't have to, but sometimes it helps. So x, we'll just make that x to the first power with respect to x. Okay, so whenever you have your x or whatever independent variable that you're using raised to the power of some real number, then that's just equal to 3 times x to the power of that number plus 1. So x to the power of 1 plus 1 divided by that same exponent 1 plus 1. Plus c. Okay, so that just equals, oh, forgot my 3. 3 times x squared divided by 2 plus c. So there's 2 in the denominator. We can factor out that 1/2 and multiply it by that 3. That gives us 3 over 2 x squared plus c as our antiderivative. All right, any questions on that one? Does that kind of make sense? All right. Okay, so let's say we wanted to find, and instead of writing out the antiderivative, they just give you the antiderivative symbol of 1 over x to the third power with respect to x. And again, the more you write this, at least in my case, the messier it looks, but that's how it's supposed to look. Okay, now with this one, you want to put it in your x to the power of some real number n form. So we're going to rewrite it as the antiderivative of x to the power of -3 with respect to x. Okay, and that integral follows the exact same rule. It's x to the power of -3 plus 1 divided by -3 plus 1 plus c. That's going to equal x to the power of -2 divided by -2. So if we factor out that -2 in the denominator, that just becomes -1/2. times x to the power of -2 plus c. And that x to the power of -2, we can move that to the denominator and make that exponent positive. That's -1 over 2x squared plus c. All right, anyone still writing? Okay. So what if we wanted to find the antiderivative of the square root of x with respect to x? Okay, so once again, whenever possible, you want to rewrite it to put it into a form you can actually use. So instead of square root of x, we're going to rewrite that as the antiderivative of x to the 1/2 power with respect to x. So that antiderivative is x to the power of 1/2 plus 1 divided by 1/2 plus 1 plus c. Okay, so we know that 1/2 plus 1, we can rewrite that as 1/2 plus 2 over 2, which is 3 over 2. So x to the 3/2 power, we'll make that a little bit neater, divided by 3/2 plus c. Okay. We don't want that fraction just sitting in the denominator like that. So what we are going to do is we're going to multiply it by the reciprocal of that denominator. So we're going to multiply it by 2/3 divided by 2/3 plus c. So if we multiply 2/3 and 3/2, that gives us 6 over 6, which is just 1. So those two cancel out and just become 1. And that 2/3, we can just factor that out to the front. So that gives us 2/3 times x to the 3/2 power plus c as our antiderivative. All right, anyone still writing? All right. So let's say if we wanted to find the antiderivative of 2 times sine of x with respect to x. Okay, so with this one, it helps to remember that the antiderivative of sine of x with respect to x is just negative cosine of x plus c. Okay, so that 2, we can go ahead and factor that out to the front. So 2 times the antiderivative of sine of x with respect to x. Okay, so that gives us 2 times the antiderivative of sine of x with respect to x. We can replace that with negative cosine of x plus some constant. We'll call that constant c number 1. So if we distribute this 2, then it gives us 2 times negative cosine of x is just negative 2 times cosine of x plus 2 times our constant c number 1. Okay. Well, 2 times a constant is still a constant, so we'll call that c. So that gives us negative 2 times cosine of x plus c. Now, these 2 steps here were really, really unnecessary, but I kind of did them to show you that how we got to the plus c at the end, even though it was multiplied by 2. But I definitely recommend just going from this step to this step. Just do your 2 times your antiderivative and just add the plus c at the end. These 2 steps here were completely unnecessary. You don't have to do those at all. This was more educational steps than actual application steps. Okay. So what if we have the antiderivative with respect to x? Okay. Well, you can rewrite that. It's just the antiderivative of 1 dx. Okay. We also remember that x to the power of 0 is equal to 1. So we can write that as the antiderivative of x to the power of 0 with respect to x. Okay, so we know that that's equal to x to the power of 0 plus 1 divided by 0 plus 1 plus c. So that just gives us x to the first power divided by 1, which is just x. So x plus c. All right, so what if we wanted to know the antiderivative of x plus 2 plus e to the power of x with respect to x? Okay, so I'm just going to rewrite it. X plus 2 plus e to the power of x with respect to x. And just like with derivatives, you can go ahead and integrate each term. And I'm going to write out each step, and you don't have to write out each individual step if you don't want to, but I'm going to write out the antiderivative of x, and that x, we can call that x to the first power with respect to x, plus the antiderivative of 2 with respect to x, plus the antiderivative of e to the power of x with respect to x. So we know the antiderivative of x to the first power is x to the power of 1 plus 1 divided by 1 plus 1. Okay. So if we get that 2 and factor it out to the front, then that gives us 2 times the antiderivative of dx, which is what we solved up here. Okay. So this antiderivative, we can't forget our plus c. And again, this step is really unnecessary, but I'm only going to do it a handful of times to show you. But you can just put the plus c at the end for all of them. Okay, plus 2 times the antiderivative of dx, which is just x, plus a constant c2, plus the antiderivative of e to the power of x is e to the power of x, plus a constant we'll call c3. Okay, so this first term, we have x to the power of 2 divided by 2. You can rewrite that as 1/2 times x squared. And this constant number 1, constant number 2, plus constant number 3, we add all those together, still equals a constant, and we'll call it c. So that's why if you have multiple terms and you're finding the antiderivative for, you can just put plus c right at the very end and not have to do it for each individual one. Okay, so we have 1/2 x squared plus our 2x plus our e to the power of x plus c. I mean, you can do a plus c for each individual one. You just don't have to. Just do the antiderivative for each one and then put a plus c right at the very end. You're good. All right. Are there any questions on this one? All right. Okay, anyone still writing? All right. A few more sheets of paper. There we go. So let's say, for example, if we wanted to find the antiderivative of negative 5x to the third power plus 4 times the fifth root of x. And make that fifth root a little clearer, just to be on the safe side. So the fifth root of x divided by 4x with respect to x. Okay, so with this one, the best thing to do if you have one like this is to simplify it as far as you can. Okay, so since you have two terms in the numerator over the same denominator, you can just split those up. That's the antiderivative of negative 5x to the third power divided by 4x plus 4 times the fifth root of x divided by 4x with respect to x. Okay, so you can see here these 4s cancel each other out. You can go ahead and cancel those out. And this x cancels out with one of these x's. So that becomes x squared. Okay, so now we have the antiderivative of negative 5 over 4 times x squared plus you have the fifth root of x divided by x with respect to x. Okay, so let's integrate each one separately. So that negative 5 over 4, we can just factor that constant right out to the front. Times the antiderivative of x squared with respect to x. Plus that fifth root of x, we could rewrite that. That fifth root of x, we can write that as x to the 1/5 power. So plus the integral of x to the 1/5 power divided by x with respect to x. Okay. Now the x squared, that's as simplified as we're going to get it, so we're okay leaving that the way it is. But this one, we can simplify it a little bit more. Because if you remember your rules for exponents, if you have x to the power of some exponent m divided by x to the power of some exponent n, that's equal to x to the power of m minus n. So applying that to this one, we have x to the 1/5 power divided by x, which we can rewrite as x to the first power. And that's just equal to x to the 1/5 minus 1. Which we could rewrite this as x to the 1/5 power minus 5 over 5. Which is x to the negative 4/5 power. So that turns this integral as an integral of x to the negative 4/5 with respect to x. Okay. So they're all in the perfect form, your independent variable raised to the power of a real number. So now we can integrate each one. So we know that the antiderivative of x squared is x to the power of your exponent plus 1 divided by your exponent plus 1. plus x to the negative 4/5 power. That integral is also the antiderivative, which is x to the power of that exponent plus 1 divided by that exponent plus 1. And instead of putting a plus c for each one of those, we just save it and put 1 plus c right at the very end. Okay, so now we simplify each one a little bit more. So we have negative 5/4 times x to the power of 2 plus 1 is just x to the third power, divided by 2 plus 1, which is 3. And make this 3 a little bit neater. Okay, plus x to the negative 4/5 plus 1. Well, we can make that x to the negative 4/5 plus 5/5, which will give us x to the 1/5 power, divided by 1/5. Plus c. I think that's the first, unless I've been ignoring it, I think it's the first time that has made that much noise. Unless I zoned it out before now. Okay, so now we don't want that fraction in the denominator. So we're just going to multiply the numerator and denominator by that reciprocal. So the reciprocal of 1/5 is just 5. So we're going to multiply this by 5/5. If you multiply these two, you just get 1. So those two cancel out and just give us 1. So here we can go ahead and simplify it one last time. So we can go ahead and multiply these two denominators. So that gives us negative 5/4 times 3, which is 12, times x to the third power, plus this 5 in the numerator, we can go ahead and factor that right onto the front, plus 5 times x to the 1/5 power, plus c. All right. Any questions on that one? All right. Anyone still writing? Okay. All right. So let's say, for example, if we want to find the antiderivative of 7 divided by x squared plus 1 with respect to x. Let's see if I can find that sheet. There we go. Okay. So with this one, we can rewrite it by just bringing that 7 and factoring it out to the front. So 7 times the antiderivative of 1 over x squared plus 1 with respect to x. Now with this one, you can't rewrite that as x to the power of some real number like we were able to do so far. But with this one, if you remember, if you go back to your inverse trig identities or antiderivatives, you have the antiderivative of 1 over 1 plus x squared. as your arctangent or tangent inverse. So this right here is just your tangent inverse. That's just 7 times arctangent of x. And actually, you don't even need the bracket. You just multiply the 7 next to it. Plus c. Or you can rewrite that as 7 times tangent inverse of x plus c. Same thing, different notation. Okay. So again, if you can, you want to write it as x to the power of a real number. But in some cases, like in this one, you can't. So you have to kind of keep your eyes open for the other antiderivative formulas that would resemble that one. Okay. So let's say, for example, if we wanted to solve the antiderivative of 10 times sine of x divided by cosine squared of x with respect to x. Okay. So again, we can look at it and tell it's not in a form that we can just plug into for our formula. So of course, we're going to have to rewrite it. And just for convenience, I always get any constants I can and factor it out to the front. So I'll just make that 10 times the antiderivative of sine of x divided by that cosine square is just cosine times cosine. So I'm going to write it as cosine times cosine with respect to x. Okay, so we can actually split those up. We can rewrite it again. Excuse me. It's 10 times the antiderivative of 1 over cosine of x times sine of x over cosine of x with respect to x. Okay, so that gives us 10 times the antiderivative of 1 over cosine of x is actually secant of x. Times sine over cosine, we can rewrite that as tangent of x with respect to x. Okay, so that gives us 10 times, and this integral should look familiar, because that's our secant of x. So 10 times secant of x plus c. So this antiderivative is just secant of x. All right, any questions on that one? Okay. So some of these you have to go back to a a few of your trig definitions. But if you have a pretty solid grasp on those, you should be okay. All right, anyone still writing? All right. Now we're going to look at initial value problems. And sometimes you might see them called, or also known as, initial conditions. Same thing. Okay, and initial value problems, you usually see that as IVP. So let's say, for example, if we wanted to solve the initial value problem, derivative of y with respect to x is equal to -5 times secant squared of x minus 2, when y of 2 is equal to -1. Okay, so this part right here, that's your initial condition. And when you see that, you know you're going to be solving for your c. So it can be just plus, you can still have the plus c, but now you know you have to go a step further and solve for the exact value of c. Okay, so let's solve this one. You know we're starting off with our derivative of y with respect to x is equal to -5 times secant squared of x minus 2. So all those times I was saying take the antiderivative of both sides, there was a reason I did that over and over and over. It's because on a problem like this, you'd actually have to do it. Here we just take the antiderivative of both sides. And if you wanted to, you could rewrite this as y prime of x. Same thing, but doesn't matter really because we know the derivative and antiderivative will cancel each other out, leaving just y. And again, if you wanted to, you could rewrite this instead of dy dx, just to give you an idea that might help. You can write the derivative with respect to x of y, where your d dx and your antiderivative cancel out, leaving just the y. But either way works. And that's equal to -5 times the antiderivative of secant squared of x minus 2 with respect to x. Okay, but we know that the antiderivative of secant squared of x minus 2 with respect to x is equal to, the antiderivative of secant squared is tangent, so that's tangent of x minus 2 times the derivative of x minus 2. plus c. Well, actually, that's just 1. I didn't have to bother writing that because that derivative is just 1. So it's just tangent of x minus 2 plus c. Yeah, that one was kind of unnecessary since it ends up being just 1. So I'll just write that as plus c. So that gives us y is equal to negative 5. And this antiderivative just becomes tangent of x minus 2 plus c. Okay. So we could see here that y is just a function of x. So you can leave it like that, or you can write it as y of x is equal to negative 5 times tangent of x minus 2 plus c. Okay. And this way is a little more helpful because now we have it in the form to where we can just plug in our 2. Okay, so we're not done yet, but we're close to it. Okay, so since we know that y of 2 is equal to negative 1, and make that 2 a little bit neater. Then we can say that y of 2 is equal to negative 5 times tangent of 2 minus 2 plus c. And we know that is equal to negative 1. Okay, so we're just going to focus on this part of it. So we have negative 5 times tangent of 2 minus 2 is tangent of 0 plus c is equal to negative 1. Well, tangent of 0 is equal to 0, so that disappears. And let me write a little side note. Tangent of 0 equals 0. So we're left with c is equal to negative 1. So now we get that value c, now that we know what it is, and we plug it into our function. So your answer is y of x, or just y. You don't have to put the y of x if you don't want to. So negative 5 times tangent of x minus 2. And instead of plus c, we're going to replace that c with negative 1. So it'll be minus 1. All right. Any questions on that one? Yes.
When finding the antiderivative of secant squared of x minus 2, was that just an application of the chain rule where you took the antiderivative of secant squared of x times?
Actually, it was u substitution, but we haven't covered that yet. That's why I kind of erased it.
Okay.
I was like, oh, we didn't cover that yet. So, but we will cover it. I believe it's 5.5 or 5.7. So.
And because we've not covered that,
yeah, that's why
we won't really find problems like this on the whole.
Yeah, you won't find it. So if you do have one like that, it'll end up just being the tangent of that same one. So it'll always be the one where it's just going to equal 1. So. All right, any other questions on that one? All right. Okay, so what if we wanted to solve the differential equation or differential equations, say for A, you have h prime of t is equal to 8t to the third power plus 5, given that h of 1 is equal to -4, and B, we have the second derivative of f with respect to x is equal to x to the -3/2 power, where we know that f prime of 4 is equal to 2, and f of 0 is equal to 0. Okay, so for these, there's a little bit of a hint. What you want to do is you want to solve for the original functions. Okay, so we have the first and second derivatives. We want to solve for the original position function. So if you have a first derivative, like A, you know you're going to integrate once. Now, if you have a second derivative, like with B, you know you're going to integrate twice. And it keeps on going in that pattern. Okay, so let's look at A. Okay, so we have h prime of t is equal to 8 times t to the third power plus 5. Okay, well, we know if we have the antiderivative of a derivative, it's just going to equal the original function plus c. So we're going to take the antiderivative. You can take the antiderivative of both sides, or you can take the antiderivative of each term. Because if you took the antiderivative of both sides, you'd still distribute the antiderivative. So the antiderivative of a derivative is just the original function. So you have h of t is equal to that 8. We're going to go ahead and factor that out to the front times the antiderivative of t to the third power with respect to t, plus the antiderivative of 5 with respect to t. Okay, so we know that our original function h of t is equal to 8 times the antiderivative of t to the third power is t to the power of 3 plus 1 divided by 3 plus 1. Plus 5 times the antiderivative with respect to t is just 5t. Remember, you can put t to the power of 0 here. And then that's t to the power of 0 plus 1 divided by 0 plus 1, which is just t. Okay. But the antiderivative of a constant is always that constant times whatever your independent variable is. So that's kind of the quick way to do it. Okay, and that is plus c. So if we simplify that a little bit more, h of t is equal to 8 times t to the fourth power over 4 plus 5t plus c. So if we go ahead and multiply this 8 times 1/4, we get the function h of t is equal to 2t to the fourth plus 5t plus c. Okay, but they did give us that initial condition, h of 1 is equal to -4. So we know that since h of 1 is equal to -4, then we know that h of 1 is equal to 2 times 1 to the fourth power plus 5 times 1 plus c, and we know that is equal to -4. Okay, so again, we're just going to look at this part of it. So 2 times 1 to the fourth power is just 2. Plus 5 times 1, which is 5. Plus c is equal to -4. So if we go ahead and combine those two, we just have 7 plus c equals -4. So if we subtract 7 from both sides, we just have c is equal to -11. Okay, so we get that c and plug it right into our function. That means we have h of t is equal to 2t to the fourth power plus 5t, and that plus c, we're going to replace that with -11. Okay, so that's the answer for 8. All right. Are there any questions on that one, or does it kind of make sense? No. All right. Anyone still writing? Okay. let's look at B. And just to rewrite it, we know the second derivative of x is equal to x to the negative 3/2 power. F prime of 4 is equal to 2. And f of 0 is equal to 0. Oh. Number 4 is equal to, make sure I wrote that. Nope, that should be f prime of 4 is equal to 2. I'm glad I did double check that. So on the first page should be f prime of 4 is equal to 2. Okay, so now, since we have the second derivative of x is equal to x to the negative 3/2 power, we're going to integrate both sides. Okay, so with this one, what you have to remember is that if you have the antiderivative of a second derivative, that antiderivative only cancels out one of those derivatives. So you're still left with f prime of x plus c. They do have double integrals, but we won't be looking at that until Calc 3. Okay, so we know that the antiderivative of this double or second derivative, since it just cancels out one of them, that leaves it as f prime of x is equal to the antiderivative of x to the negative 3/2 power with respect to x. So we know f prime of x is equal to, and the antiderivative of x to the negative 3/2 power is x to the negative 3/2 plus 1 divided by negative 3/2 plus 1. Plus our constant, we'll call it c number 1, but only because when we do the antiderivative again, we'll have another plus c. So we can't have them all called c because they could be different values. So we call it c number 1 and c number 2. Okay, so we know that negative 3/2 plus 1, that's just negative 3/2 plus 2/2, which is negative 1/2. So we know that this is going to simplify to f prime of x is equal to x to the negative 1/2 power divided by negative 1/2. And you leave a little bit of room after that, plus c number 1, or constant number 1. Okay. So again, we want to get rid of that negative 1/2 in the denominator. We don't want that making this problem harder than it needs to be. So we're going to multiply the numerator and denominator by its reciprocal, which is negative 2. So you have negative 2 divided by negative 2. Okay, so this negative 1/2 times negative 2, that just cancels out and becomes 1. And this negative 2 in the numerator, we can just move that right on over to the front. So we have negative 2 times x to the negative 1/2 power. So we can rewrite that has f prime of x is equal to -2 divided by square root of x. So we can rewrite that by moving that to the denominator. So I'll make this a little bit smaller. So -2 divided by the square root of x plus our c number 1. Okay, now if we look at our first initial condition, we know that since f prime of 4 is equal to 2, it means f prime of 4 is equal to -2 divided by square root of 4 plus c number 1. And we know that that is equal to 2. Okay, so again, we're just going to look at this part of it. That gives us -2 divided by the square root of 4, which is just 2, plus c number 1 is equal to 2. So this is just -1. So if we add 1 to both sides, those two will cancel out. So we know that c number 1 is equal to 3. So we get that and plug it right into our function. So f prime of x is equal to -2 divided by the square root of x plus 3. Okay, so we were able to find our first derivative. Now we have to take the antiderivative of that to find our original function. And kind of separate that a little bit. Okay, so since we know that f prime of x is equal to -2 divided by, well, instead of divided by square root of x, just to save a step, we'll write that as -2 times x to the -1/2 power plus 3. Okay, so once again, we take the antiderivative of each term. Okay, so the antiderivative of the derivative in this case is just the function f of x. Is equal to -2 times the antiderivative of x to the -1/2 with respect to x plus the antiderivative of 3 with respect to x. Okay, so we know that f of x is equal to -2 times the antiderivative of x to the -1/2 power. That's x to the -1/2 plus 1 divided by -1/2 plus 1. plus the antiderivative of a constant is just that constant times the independent variable. Okay, and plus C, but we're going to call that C number 2. Or you can call it C since it's the last one. We just couldn't call this one C and this one C. But if you call this one C number 1 and this one C, that would have been just fine. Ooh. So that means we have f of x is equal to -2 times x to the power of -1/2 plus 1 is +1/2. X to the power of 1/2 divided by 1/2 plus 3x plus C number 2. And we'll finish it on the next page. All right, anyone still writing? All right. Okay, so I'll just rewrite where we left off. F of x equals 2 times x to the 1/2 divided by 1/2. And I'll leave a little bit of room after that. Plus 3x plus C number 2. And we left a little bit of room because we want to get rid of that 1/2 in the denominator. So we're going to multiply it by its reciprocal. So we're going to multiply it by 2/2. Or you can say 2/1 divided by 2/1. So we know 2 times 1/2 is 1, so those two cancel each other out and just become 1. And this 2 right here, we can just move it to the front and multiply it by the 2 that's already there. So we have f of x is equal to 2 times 2, which is 4, times x to the 1/2 power, plus 3x plus C number 2. Or instead of x to the 1/2 power, you can write it as square root of x, which might be a little bit easier. So 4 times square root of x plus 3x plus our constant number 2. Okay. Now we know that f of 0 is equal to 0. So since f of 0 is equal to 0, that means that f of 0 is equal to 4 times the square root of 0 plus 3 times 0 plus our constant that we called C number 2. And we know that that f of 0 is equal to 0. Okay. So again, we're just going to focus on this part of it. So 4 times square root of 0 is 0. And you really don't have to write this part. You say 0 plus 3 times 0 is 0. Plus C number 2 is equal to 0. You could have just wrote C number 2 is equal to 0, and that would have been fine. So now that we know what C number 2 is equal to, we just go ahead and plug it right into our function. We know that f of x is equal to 4 times square root of x plus 3x. You can put plus 0 or you can leave it blank, up to you. Or just f of x is equal to 4 square root of x plus 3x. Either one of those work. I think I caught a little error. Let me double check to make sure. Nope, actually you're good. Just making sure. Yep, oh, never mind, there it is. I knew something didn't look right. When I rewrote it, I forgot to put my negative. So all you have to do is just make those negative. I know something bugged me about it. There we go. So that should be negative 4. There we go. All right, any questions on that one? All right, so we will go ahead and stop there since that's the end of chapter 4. Let me see, let me double check something really quick. All right. So the chapter 4 test should be posted in about 20 minutes. So you will be able to start on that. And then tomorrow we will start on chapter 5. So we have chapter 5 and section 6.1, and that'll be it. But chapter 5 it starts off a little rough, but it kind of eases up a little bit later. But the first 2 sections are a little bit rough. So I don't want the first 2 sections to scare you too much, but it eases up after that.
I'm able to fill out a form to see if I can borrow a computer. So hopefully I'll be able to do that and then take the exam.
Oh, okay.
I don't have any other computer I can use in my house.
All right. If you can't borrow one, what you can do is go to the testing center, and and they can do that too.
But I actually called them yesterday and they said that I could do that and they would have a computer in a few days.
Oh, okay.
For me to borrow, and then hopefully I'll be able to finish everything by Saturday.
Okay.
If I get my computer on time.
All right.
Yeah. Have a good day.
You too.
So I'm gonna be missing the latter part of next week because I have summer orientation.
Mm-hmm.
Is there anything I can do to get ahead, or anything I should worry about for the homework and stuff?
Pretty much as long as you have access to your computer and you can do everything online, you should be good.
So the thing is, I won't be able to from Wednesday to Sunday, I won't be able to walk. Like I'll be driving up, which is
Oh,
a
okay, I see what you're
12-hour
saying.
drive,
Oh, okay, I see what you're saying.
and then it's
yeah.
up there, and then so
Oh,
I'm
yeah.
not gonna have time to like really watch the lectures. Is there a way that I could do that beforehand?
Oh yeah, what I can do is I can open up chapter 5, and this way you can just go ahead and start on it early. If
And then
you
would
like.
you have any videos, or would the Friday videos be adequate for that? Because I know that David Friday does a pretty good job on the
Mhm.
lectures, but
Yep. So with those, yep, yeah, I believe he does have those
Okay.
available. So you should be able to access his videos.
Okay.
From there also.
yeah, okay, I
All
appreciate
right.
that.
All right. You're welcome.
I
Hello.
just have a question for these.
Sure.
Final exam practice.
Mhm.
Are these like extra credit, or are they like for credit? Because I know some professors like they do like these are like extra credit.
Yep. Those are extra credit.
Oh, these are extra.
Yeah.
Credit. Okay, gotcha. Thank you.
You're welcome.
There's no chance we're allowed to use our lecture notes on the tests, are we?
You will be allowed to use an index
I know
card.
the index card.
Yeah,
for the
that's
final.
that's all you'll be able to
Nice.
use. I know always.
It's fine, I was just double checking,
Yeah.
because there's a lot to remember from
It
this
is.
section, but
And I used to, before they went to departmental finals, I used to let people bring like a whole sheet with whatever they want. But with the departmental final, they have like their own set of rules. So
aren't
can't do
we allowed, or not allowed, but given some formulas on the final,
that.
I think?
I want to double
Because
check.
I know I've been given a small amount for my previous
Let me
math classes, and I'm just
see.
curious.
They have a practice packet, which kind of gives you.
Mhm.
Trying to remember if they do or don't. Nope, I don't think they do.
If it's anything like my last classes, it would be a little bit below here, as it would say this is provided and this is not, but it doesn't
Yeah.
look like it, does
It
it?
goes right from the explanation to the
Mhm.
question, so I don't
Okay,
think they provide any.
so write very small on my index card.
Yeah,
Have a good day.
you too.